the stuff on my like practice thing. It's like just stuff I can like tell you.
Okay, that's fine. Yeah, that works for an awful lot of math. Only time it might not work is if there's a graph involved that they want you to interpret.
Yeah. So I'm just start from the beginning of the packet and go. It's like 2 to the power of x equals 21, and they just want you to do it in log form, which I forget how to do logs because like I only did it for like a week and then I forgot.
This is, first of all, this is an exponential equation. It's not an algebraic one. There's no way to figure this out on your calculator if you do not use logs. Okay? Now, the only real thing you have to remember about logs is that they are exponents. So what goes on the other side of that equal sign?
Exponents?
Logs are exponents. So the other side of that equal sign has to be this exponent, x. Now, there's two other numbers. Where's the 2 go? Where's the 21 go?
Does the 2 go, say where it is, like in the front of the log?
It's the base. It's the base. The 2 is the base, which only leaves one spot for the 21, which I call the argument. Okay? So these two are equivalent.
Okay.
Okay? Now, you have to go both ways. In other words, you're just as likely to be given the log expression and they want you to do the exponential expression. Well, I have a nice easy way I remember it, which is the number on the far left raised to the power of the number on the far right equals the number in the middle.
Okay.
So if I was going the other way, it would be 2 to the x equals 21.
Okay. So it's like, so if it's asking writing log form, I just put what you put in a log.
Yes. In other words, every exponential equation has an equivalent logarithmic equation.
Okay.
Okay? So what else do you have?
Yeah, I have another one of those. It's like, I think I can sort of figure.
Well, go ahead and give it to me and I'll have you do it and we'll make sure you get it right.
Okay, it would be e squared equals 7.4.
E squared?
Yeah.
Okay. What are we supposed to do with this? Put it in log?
Would it be a natural log because it's e?
Well, yeah. In other words, I could do this. I could say the log has to equal 2, right? E is the base. 7.4 is the argument. And now that is the same as natural log. So I would write it like this. That's all natural log is it's the log base 2. Hold on one second. Let me close this door. I don't know. I feel like I'm yelling. Do I sound like I'm yelling when I'm talking?
Not that much.
No?
It's fine. It just sounds like you're projecting voice.
Well, it's part of it is probably because of my phone. I feel like I have to talk a little louder. But all right, what else you got?
I think the exponential form, like it'll sort of, let's just do them.
Yep.
Like the log base 6 and 36 equals 2.
Put this into exponential form.
Yeah. Would that be,
number on the far left raised to the power of the number on the far right equals the number in the middle.
So it would be 6 squared equals 36.
Is that a true statement?
That makes sense. I wasn't even thinking about it, like,
Yeah.
logically.
Well, of course, right. In other words, you wouldn't want to come up with 2 to the 6th power equals 36. So, but a lot of times these aren't going to be easy. In other words, if I put a 5 there and I say this is x, in other words, what the heck? That means that 6 to the x equals 35, and x is not an integer. It's some number between 1 and 2. Go ahead. What else you got?
I have like another one of those, but I think in order to do it, it would just be e squared. ln x equals 27.
Oh, you lost me. ln x equals 27. Okay, I see what you were doing. You were doing the answer. Okay, put that in exponential.
Yeah, that would be like e to the
Number on the far left raised to the power of the number on the far right.
e to the 27.
Equals the number in the middle. What's the number in the middle?
X.
That's what x is. And you could get this number off your calculator.
Yeah.
So you could solve for x here. Hold on, I'm getting messages that I need to close out some of my applications. Let me close out that one. That should help a little bit. All right, what else you got?
I like simplifying problems. I'm just gonna want to do the whole packet.
That's fine. Let's start from 1 and go on. If they're simple and you can do them, we'll get rid of them quick.
Okay, this is one's like a simplification problem. It's like 5e, 15e to the third.
15e to the third.
And then that's over 25e to the second.
And that's it? We're just supposed to simplify that?
Yeah.
Okay, let's do the numbers first. In other words, you can take these one thing at a time. Do the numbers first, then do the next variable you run into, or the next number, and so forth and so on. So these are simple. They could have 6 different variables in the numerator and the denominator, and you just do them one at a time. What's 15 over 25 simplified to?
Doesn't it simplify to 3 over 5?
What's e to the third divided by e to the second simplified to?
Wouldn't you get rid of e on the bottom and just e on the top?
Subtract the exponents. So it's e to the 1, yes, which is just e.
Yeah.
In other words, whenever you divide something that is a power of 1 less, then you're always going to end up, and that's in the numerator, incidentally. I've written it in the middle, but I could have just as easily written it like this.
Yeah.
Okay, what else?
And then the next one is just the same, but it's like 27e to the x over 9e to the 5th.
What are the numbers?
It would be 3 on the top and like 1 on the bottom.
Just 3 on the top is all you need.
But like basically like the 1.
Now what is this equal to?
Would it just stay the same because you don't
What do
really
you do when you're dividing same base, different exponents? What do you do? In other words, if I had this problem here, 3 to the 7th divided by 3 to the 5th, what would the answer be?
Do you subtract it pretty much?
Always. Not pretty much. Every time.
Wouldn't that just be, you just put e to the...
Just like that.
Oh, you just put it up there.
Uh-huh. Yep. That's the only way to really do it. In other words, because we haven't solved for, they didn't ask us to solve for anything here.
Well, technically you could just keep it on the bottom, but like it's more simplified if you put it on the top.
Yeah, technically you would not want to keep it on the bottom. In other words, yeah, the whole purpose of this problem is to simplify it. So if you kept it on the bottom, you wouldn't be simplifying. Okay, what else?
There's this one that's 3e to the 11th times 8e to the 3rd.
Do the numbers first.
And then it's like over 12e squared.
Okay. There's multiple paths you can go here, but let's do the numbers first. What's 3 times 8 divided by 12?
Would it be like 2 on the top?
Now, let's combine the e's on the top first before we do anything. In other words, we've got to do one thing at a time here. What does the e's on the numerator become?
It becomes 14.
E to the 14th, and I'm dividing that by e squared. In other words, I lost the 12 already.
Okay.
Okay, so what's this?
It would be just 12 on the top.
2e to the 12th. That's what I'd like you to say when I say, what is this answer? Is give me the answer, okay? All right, what else we got here?
There's like finding inverses.
Okay, let's do it.
This one's y equals log x plus 4.
Like this?
Yeah.
Okay. So there's 2 steps to finding an inverse. What are they?
You switch the x and y.
And what's the second one?
You solve for x.
Solve for y.
Oh.
In other words, once you've switched the x and the y, it's solved for x. What it's not solved for is y. Okay. So now I got to solve this thing for y, which is not that easy. Here's a rule about logs.
Okay.
If I have the log base b, if I have b raised to the log base b of x, what do you suppose that's equal to? In other words, that's an exponent. The whole exponent is log base b of x. And that's equal to x. So as long as this base is the same as this base, then the answer is whatever that argument is. Okay? Now, in this problem, we have to do something you're probably not used to doing, which is to make the left and the right side of the equation be exponents to a number. And how am I going to pick that number? It's going to be 10. Why? Because this log is base 10. If it doesn't show a base, it's base 10. And now notice what this is going to become. What is 10 raised to the log base 10 of y plus 4? Remember, what was b to the log base b of x equal to?
B to the log base x.
It's equal to the x. In other words, these effectively go away.
Oh, I see what you're saying now.
Okay, so that's why I took the left and the right side of the equation and made them be exponents. And you can do that. If I have a, let me just put a hypothetical here. If I say a equals c, well then 9 to the a power is equal to 9 to the c power. I can always do that. Just like you could go the other way. If I had 9 to the a power equals 9 to the c power, well then I would say, well, a is equal to c. So if I start with a equals c, I can drop any base I want underneath both sides of the equation. Okay? It's a neat little trick for solving problems like this. Because now I've got 10 to the x power on the left, but this effectively disappears, and what I've got on the right is y plus 4. So what's y equal to?
Y is equal to x to the 10 to the x minus 4. Or I guess
that's it. That's the answer. The only thing is it's not really correct to call it y anymore. That is y inverse. In other words, y was that thing. Okay? What we just solved for was the inverse of that thing. So we can't really call it y. You got to call it something other than y. In fact, once I switched the variables, it would have probably been correct to label that like that. It's just confusing when you do it that way to a lot of people. So I don't really put that inverse on there until I get to the end. Okay?
We have like a couple more of those.
Okay. What is it?
Y equals 2 to the x plus 1.
Work me through the steps. What's the next line I should write?
The plus 1 is in the exponential.
What's that?
So plus 1 is with the exponent.
Ah, excuse me. It's the one advantage of reading the problem instead of verbalizing it. But that's okay. It's good for you to learn. In other words, that's 2 to the left paren x plus 1 right paren power. That's how I would say that. Okay, so what's the next line? Finding the inverse.
You just switch the x and y.
And now what? How do you solve for y? This is the key. This is now an exponential equation because the thing I'm trying to solve for is in an exponent. So this is not particularly easy to solve for. You cannot use algebra to solve for it. You have to use logs. Whenever you have an exponential equation, 99% of the time, you're going to have to use logs to solve it.
Yeah.
Okay? Now, which log? I always use natural log. I'm going to take the natural log of both sides. And there's lots of different logs you could take, but the natural log works just fine and just as easy as any other. Okay? So now is what I got is this. And it's correct. It's correct to be able to take the log of both sides. You can always do that. You can do anything you want to an equation as long as you do it to both sides. Now there's a property of logs. What can I do with that that's vital?
You can put it by itself.
I can move it down in front to there.
Oh, yeah.
That is maybe the most valuable property of logs, is that you can take an exponent and move it to the front, and very important that you put parentheses around it. In other words, that is correct. The way I've done it, it's a correct progression of solving this. Now what's the next step? Still trying to solve for y.
Get rid of the natural logs.
How do I do that?
Do you take the inverse? Or?
No? You're not really getting rid of them. This natural log of 2 over here, that's a number. We can look in our calculator and figure out what that number is. So all that is a coefficient. How do you get rid of coefficients?
You just move it to the other side.
By doing what?
Subtracting them.
What is that coefficient doing right now? Is it multiplying?
No.
Yes, it is. That natural log of 2 is multiplying this y plus 1. That's why I put parentheses around the y plus 1, is because it is multiplying the natural log of 2. So, to get rid of the natural log of 2, I got to divide both sides by natural log of 2, which is just a number. That's all it is. Okay? Now that's going to do that. So now I'm almost done. I've got y plus 1 equals this thing on the left, so y is going to equal natural log of x divided by natural log of 2 minus 1. And now I go in and I put in the inverse sign. That's what the inverse of that original function is. Okay, what else?
There's another one that's y equals 3x plus 8.
Just 3x plus 8 like this?
Yeah.
Next line?
That's it.
No, read me the next line that I'm supposed to write.
That's it.
Huh?
Like,
You're supposed to find the inverse of this, correct?
yeah.
How do you find the inverse?
You just switch in.
So read me the next line, Sam.
Well, that's the whole problem.
I know. I want you to do the problem, and I want you to tell me what to write next.
I'm sorry about that.
That's okay. I knew that there was some miscommunication going on somewhere.
Yeah, you just switch in like 3y
No?
plus 8. X equals 3y plus 8.
Okay. That's what I wanted from you.
Yeah, my
In other words, just saying switch the variables, I want to make sure you can write the proper equation. Just telling me to switch the variables, that doesn't tell me much. Okay, now what?
You divide it by 3.
Not yet. Usually you want to get rid of stuff that's being added or subtracted first. Notice here's the problem with dividing by 3. I got to divide that by 3 also. And then I got to divide that by 3. Okay? So it's a little more difficult if you get rid of multipliers before you get rid of stuff being added. The 3 is a multiplier. The 8 is being added. Okay? So first let's subtract 8. Now what?
And now you can divide it by 3. Right. Y by itself.
Right. And that's going to be y inverse, and it's x minus 8 all over 3. And there's your answer. Now, that's actually what I would have come up with, even if I did it the original way. Or not the original way, the way you suggested, where I divide by 3 first. It just makes it a little harder. You notice that immediately we're dealing with 8/3 as a fraction. Nobody likes dealing with fractions. So it's just easier to go this kind of progression. Get rid of what's being added and subtracted, then get rid of what's multiplying or dividing.
Okay.
All right. What else?
So the next one I have is log is 5.
I didn't quite understand what you said. Say again?
It's log base 5 of 125.
And they just want you to evaluate that?
Yeah.
Okay.
Like
You get a lot of problems like this. The easiest way to solve these are to add a variable, is to make up, that's equal to something. They're asking us what is x, right? Okay. Now, take this logarithmic equation and convert it to exponential. What's the exponential expression here?
The exponential expression is
Number on the far left
5.
to the number on the far right, power.
Okay, 5 to the x equals 125.
Okay. Now what's x? You don't need a calculator for that.
X equals 25.
5 to what power is equal to 125? What's 5 squared?
5 squared is 25.
What's 5 cubed?
5 cubed is 125.
And x is 3.
Oh, that makes
Okay.
okay.
Now, if you're always used to doing these from this position, it's actually easier because it's really easy to convert these to exponential expressions. It's the number on the far right raised to the power on the far right equals the number in the middle. But if all of a sudden you get presented with this problem, people have a hard time making that adjustment. That's why I say always make up a variable and let this expression equal that variable and then convert it to exponential. You know how to do that and then solve it. So, all right, what else you got?
I have a lot of other ones of those, but like I can sort of
Well, let's do
that.
a few of them. Let's make sure you know how to do them. I mean, we don't need to skip any. Let's make sure you can do 2 or 3 in a row, all on your own, and then we can skip some.
Okay, what's log 100?
Okay, tell me how you're going to do this.
Do you divide everything by 10?
Nope. What did I say the first step should be?
Put it in exponential form.
No, you're not dealing with an expression yet, so it's hard to put it in exponential form. If I add a variable, we're going to make that equal to x. Now you can put it in exponential form. What's the exponential form now?
Would it be log, would it be 10 to the x?
Equals what?
Equals 100?
What's x equal to?
X is equal to 10.
10 to what power is equal to 100?
10 to the second power.
Then x equal 2, not 10.
Yeah, that makes,
In other words, you got to be able to solve that right there, always. In other words, getting it into exponential expression is just the first step. But most of these they give you are going to be such that the answer is always going to be a small whole number. It's either going to be 2, 3, 4, 5, maybe sometimes a minus number, but you got to be able to do that right there. You got to be able to know how to do that.
okay.
All right. But notice that this wouldn't have been that easy if I don't introduce the x. In other words, now the problem is, well, 10 to what power equals 100?
Yeah.
Well, the answer is 2. But it makes it a lot easier if I introduce the x, and now I just write it out and then solve it. Okay, what else? Let's do one more of those. Another log.
Okay. Log base 27 of 1.
Log base 27 of 1.
Yeah.
Okay. It's the first step.
Make it equal to x, I guess.
Second step.
Like, put it in exponential form,
Do it.
which is like 27x.
Hold on. It's not 27x. 27x would be that.
27 to the x.
There you go. It's 27 to the x power. And you can shorten that to 27 to the x equals what?
Equals 1.
Now, think about that for a second. what's x got to be?
0 is 0.
Yeah. Any number to the 0 power is equal to 1. Any number. Which means that the log of 1 is always 0, no matter its base. In other words, if I go over here and I say the log of some unknown base of 1, that's always 0. Does not matter what the base is, because b to the 0th power is equal to 1.
Okay.
Okay? So always remember that the log of 1 is 0 regardless of what the base is.
Okay.
Okay, what else?
This one's log to the base 1/4 is 16.
Okay, tell me what to do.
You make it equal to x.
Next.
Then
Same thing, it's nothing different. Just because that's a fraction, it doesn't matter.
yeah, you turn it into exponential form.
Right, so what's the next line?
Would it be it would be 1/4 x
No.
equals 16.
If I write it the way you said it, that's what I would write. You said 1/4 x equals 16.
1/4 the x equals 16.
There you go. Now, this is a little bit more difficult to solve.
Yeah.
If that was 4 to the x equals 16, what would x be?
4.
If I had 4 to the x equals 16, what is x? Think about these. These are not multiplication. And that's, I think, where you're getting confused, even verbally. You want to keep indicating it's multiplication. It's not. It's exponentiation. So 4 to what power would equal 16?
4 to the second.
Okay. Now instead of 4, we got 1/4. So it ends up being 1/4 to the minus 2 equals 16. Let me just show you how I got that. First of all, negative exponents don't mean negative numbers. They just mean reciprocal. Okay? So if I wanted to write that, the way I would do it would be I would put 1 over 1/4 to the positive 2. In other words, that is the same as that. You see why?
Yeah.
Now, 1 over 1/4 squared is 1 over 1/16, which is equal to what? How do I solve that?
1/16.
I'm dividing 1 by 1/16. How do I come up with that answer?
4 to the negative.
How do you divide by a fraction?
Do a negative.
Not negative. You multiply by the reciprocal. It's not a division problem even. We turn it into a multiplication problem. So it becomes 1 times 16 over 1, which is 16.
Okay.
So that's why 1/4 to the minus 2 equals 16. So when you're dealing with fractions, the way to kind of think about them is figure out what 4 to what power would be equal to 16. Whatever power you come up with, use the negative power. Okay? These are a little tricky though. If you've got another one, let's keep doing these because they're going to get harder. I want to make sure you can do the hard ones.
I just haven't done this in like 4 months. So
That's okay. No, I'm not complaining. I just want to make sure that we get you prepared for your final. When is your final? Is that what we're preparing for here?
Yeah, it's like next Wednesday.
Okay.
So like still some time.
Okay.
Okay, so log base 9 to the 9 to the 2.7.
Log base 9 of 9?
Yeah, to the 2.7.
Like that?
Yeah.
Exactly like that?
Yeah.
Okay. What's the first thing I can do here?
Put it into
You could add the x, but that's not really going, yeah, it does help. Okay, now put it into exponential. It's not really the way I want you to do it, but this will work. Put it into exponential.
So it'll be 9 to the x equals 9 to the 2.7.
Now what is x?
The x would be x equals 2.7.
Yep. So that's not a bad way to do it. That was a pretty quick way to solve it. But there's something else that's worth noticing here. And that something else is remember I said the most powerful rule of logs is where you can take the exponent and put it in front?
Yeah.
So this expression really is 2.7 times the log of base 9 of 9. And what is that always equal to when the base is the same as the argument?
It's equal to 0?
1.
Oh, 1. Okay.
This is always 1. The log of 1 is always 0. But this is equal to 1, which means our answer is 2.7.
Okay, that makes sense.
Well, and I think this is probably a better way to do it, because this forces you to realize that the log base b of b is always 1. Always. No matter what the argument is, no matter what the b is. If this number is the same as that number, then that answer is 1. Automatic. Okay, what else?
The next one is log base 3 to the 27 to the 2.
Log base 3 of 27 to the 2, like that?
Yeah.
So what's the first thing I should do here?
You make it equal to x.
Okay. Now what?
Then you turn it into exponential form.
Okay, give it to me.
It would be 3 to the x equals 27 squared.
Okay, now that's not the same as that, but they have a common exponential base, and by that I can write both of these numbers as powers of 3, correct?
Yeah.
Okay, I don't need to change the one on the left, it's already a power of 3, but I'm going to write 27 as 3 cubed instead of 27. You with me?
Okay. Yeah.
Now, apply the rules of exponents. What's the right side become?
The right side has become 3x equals...
Now, hold on. Yeah, okay, go ahead.
3x equals 3.
How do you handle exponentiation when it's a double exponentiation?
You multiply.
Okay, correct. So what is this right side?
6.
Okay, now what's x?
X equals 6.
Yeah. In other words, once I've got the same base, now I can equate the exponents. I couldn't do it as long as this was a 3 and that was a 27. But as long as I can turn both of these numbers into powers of a common base, in other words, if that was a 9, then I would write the left side as 3 squared to the x, and the right side is 3 cubed. In other words, my common exponential base is 3, not 9.
Right.
Okay? What else?
Yeah, sorry, my dog started like going crazy.
That's all right. Man, that's all right as long as there's not a serial killer trying to kill you, and she's warning you.
Yeah, I hope he's not trying to kill me.
You never quite know what's going on with dogs when they go crazy like that. So.
Yeah, there's some crazy creatures, you know.
Uh-huh. So what else we got, Sam?
We have e to the natural log of 6. Doesn't the natural log and e cancel?
In this case, yes. In other words, what I really have is b to the log base b of 6. So, yes, this is equal to 6.
Okay.
Well, that's what this is it's e to the log base e. That's what natural log is of 6. So that's equal to 6 also. As long as this is the same as that, then your answer is always whatever the argument is.
Okay.
Okay?
Okay.
Sometimes it makes the problem a little easier if instead of writing natural log, you write log base e, like that one. That was easier to figure out if I wrote log base e instead of natural log. Okay, what else?
7 to the log 7, 18.
What's that equal to?
Was that the log 7 cancel?
Uh-huh.
7,
that's b to the log base b. So that's always equal to whatever the argument is.
Okay.
If I had this, let's make it a little more complicated. What's that equal to?
Would it be equal to 36?
No? In other words, this is the same as that. So what is it equal to?
It'd be equal to 1.
The argument. What is the argument? That's the argument.
Oh, I see.
It's equal to x squared minus 14. In other words, it's not just equal to a single number all the time. You can have all kinds of complicated expressions as arguments to the log that is in the exponent. And what I'm trying to say here is it doesn't matter how complicated your expression is. Whatever it is, that's the answer. As long as that is the same as that. The answer is always the argument of the log that's in the exponent. Okay, what else?
The next one is using the change of base formula.
Okay, that's pretty easy. What's the log expression?
So it says do that in the calculator, so we don't even have to do that.
No, hold on. You want to make sure you know the change of base formula.
I don't even need to use that because it's in my calculator by itself.
So you have a calculator button that lets you do log of 5 base 7?
Yeah. So it's sort of unnecessary.
Okay. It's real easy to remember the change of base formula, Sam. I'd like you to remember it whether you can do it in your calculator or not. It's that easy. In other words, it's the log of the upper number divided by the log of the lower number.
Okay.
It's that simple. And now this you can do on any calculator, even if it only has 2 log keys on it. Okay? So it's actually almost easier to do it this way than it is to do it on your calculator where you have to put in a base and an argument. All right. That's the change of base formula. It's that simple. In other words, the log base b of c is the log of c divided by the log of b. That's how simple it is.
Okay.
The upper divided by the lower. Okay, what else?
This one's like expanding expressions.
Okay, you're going to have to expand and condense. Let's do a few of each.
So log 4x to the fifth is the first one to expand.
I'm sorry, I didn't quite hear that. Log of what?
Log 4x to the fifth.
Okay. There's three basic log rules that are involved when you're expanding. You know the three of them? Here, let's go through them. I'm going to write them, but then I'm going to erase them because I want you to memorize them. I don't want you to just look at my page to figure out how to do it, because what happens is you don't memorize them when you do that. You got to memorize these. Notice what the first one means. If I'm multiplying in the argument, then I'm adding two different log stuff together. The two things that are multiplying together. Okay? Here's the second rule, and this follows. In other words, if I am dividing in the argument, then I am subtracting those logs.
Okay.
With me? So those two are pretty easy. And the third one is the one we've dealt with already a few times. If I am double exponentiating, then I'm multiplying.
Yeah.
See what that third one does?
Yeah.
Okay. Now I'm going to erase those. You got them memorized?
Maybe. I think I do, but I might forget exactly which one.
That's okay. Just remember, it's real easy to memorize these. And the reason is that it's very similar for exponents. The rules for exponents are the same. If I'm multiplying, I'm adding the exponents, right? If I'm dividing, I'm subtracting the exponents. Well, remember what I said? Logs are exponents. Logs are exponents. So if I've got 5 to the 4th power and I'm multiplying it by 5 to the 7th power, I'm adding the exponents. Well, that's what I'm doing there. Logs are exponents. So if I'm multiplying inside the argument, I'm adding two separate log functions. All right, take a look at them one more time, because the second one is just kind of the same principle as the first one. The third one, you got to memorize that. You can always take that exponent and put it down in front on the algebra line. All right, let's tackle this first problem. Let's expand it. What do we got going on inside? First of all, let's do something with that exponent. Or not yet. Let's do that as the third step. What we got going on here is multiplication. We're multiplying 4 times x to the 5th. So if I want to separate this into two log statements, what would they be?
Would it be log 4 plus log x to the 5th?
Good. Now one more step to fully expand it. It's not fully expanded as long as I have an exponent over there. So fully expand it. What can I do with that 5?
You can put it out front.
Now, notice the 5 only goes in front of that log expression. It doesn't go in front of the first one, because the 5 did not apply to the 4.
Yeah.
It would have been different had we had that. In other words, if that would have been the problem, then I would have brought the exponent down immediately, and I would have made it 5 times log of 4x, And that's equal to 5 times log of 4 plus 5 times log of x. So be careful with these exponents that you always know what that exponent's applying to. And in this case, it was only applying to the x. So I split them apart first, and then I brought the 5 down. So it only was in front of the second log expression.
All right.
Okay, what else you got?
The next one is natural log of 2x cubed over y squared.
No, I get it. It's going to be an expansion, so that whole thing has to be in the argument.
You good?
Like that?
Yeah.
Okay. Let's do the exponents last in terms of expanding it. Let's expand it into the sum and the difference of some stuff.
Okay.
So let's take the numerator first. Split that up.
So it'd be ln of 2x cubed.
Hold on. We've got 2 multiplied by x cubed. That's multiplication going on. Let's split it up.
Okay, so it'd be ln 2 plus ln x to the 3. And then you'd subtract it, right?
Now we'll handle the bottom.
Yeah, ln is y squared. Yeah.
Okay, so that's the first step. Now let's take care of all those exponents. What's the next term?
It'll be ln 2
Hold on. Okay, go ahead. Yeah.
plus 3 ln x minus 2 ln y.
You got it. Okay. Now, we don't have that much time, so let's make sure we do a few condensing.
Yeah, I have 2 of those.
Okay, let's do them real quick, as fast as we can here.
Okay.
Because you're going to have to do an equal number of them. In other words, you're going to have to do as many expansions as condensing. So they're the opposite sides of the same coin.
Okay.
So give me the expanded expression, and then we'll condense it.
Okay, so it would be 2 parentheses log 15. And if for some reason on my packet it doesn't have a multiplication, I'm guessing it's multiplication sign. Because it's like...
Actually, if I don't put anything, multiplication is presumed. So I don't need a parentheses there. That's 2 log base 10 of 15. What else?
No, but there's the log thing after it. It's in between. But it's not like... It's in parentheses and then there's log 3. But there's no sign in between it.
All right, I'm a little confused. Can you verbalize how I should write this?
Yeah, you had it right, log 15, except like before, after the 2, you just put a parenthesis. And then it's like, for some reason, there's a blank on the handout.
Like this?
Log. And then there's like something after it where it's a blank because I think you made a mistake.
Let's do one where you don't have blanks.
Okay,
we can't do a problem if you don't have the problem on you.
Okay, so it's 4 natural log x plus 6 natural log y.
Okay, turn that into 1 log expression.
Okay.
One at a time. You don't have to do the whole thing all in one step. Let's do it in partial steps. And this time go backwards in the same order you went the first time. In other words, deal with that leading coefficient first, not last. When you're expanding, you deal with the exponents last. But when you're condensing, you deal with the leading coefficient first.
So it would be natural log of x to the 4th plus natural log of y to the 6th.
Good. Now put that into a single log expression.
it'll be natural log of x to the 4th, y to the 6th.
Perfect.
Okay.
Got another one?
No, I don't have any more.
Okay. Let me just make up one. There's one little hitch that can happen that you should be aware of.
Okay.
Put that, expand that.
Is that a square root sign?
Uh-huh.
Okay. Would it be log, that would be equal to log x to the negative 2, so that means
Hold on. No, it isn't. It'll equal to log x to the 1/2. The square root sign means a power of 1/2.
Wouldn't that be the same as negative 2 that I was doing?
No, it's not. Square root is not. Negative 2 would be 1 over x squared. That's what negative 2 would mean.
Oh.
This is not the same at all. X to the 1/2 means square root of x. This means 1 over x squared. They're not the same number at all. Okay? So the reason I brought this problem up is because radical signs don't work very well in log problems. So I don't want you to be thrown when they give you one that's got a radical sign in it. Okay? Because all you do is convert it to a fractional exponent and then apply the rule where I can bring the exponent down in front. So there's your answer. Fully expanded.
Okay.
Okay? And if they give you cube root, what would that be? Log of x to what power?
To the 1/3.
Yeah. Okay. As long as you can convert radical signs to fractional exponents, you're in good shape.
Okay.
Although they didn't give you any like that, so you may not have to do that, but it's worth knowing.
Yeah, that's true.
Okay? You good to go? You got another one or two you want to do?
I don't have any others, so I might as well just save the others.
Okay. I'm sorry, did you say we might as well end it, or what'd you say?
What did I say? I said there's no other problems like that, so we might do that.
Okay. Sam, have a good rest of your weekend, and if you want to schedule something for next week,
sure.
I've got availability, and especially early in the morning. That 7:30 time actually works really good for me. I don't know how well it works for you, but if you can't find any other time, if I bring my schedule up here for next week, let me just point out to you what I've got available. Hold on a second. Your test is Wednesday?
Yeah, let's set one for Tuesday at 7:30 a.m.
Okay. I'll do it.
Yeah, thank you. Appreciate it.
You're welcome. I'll talk to you Tuesday at 7:30.
Okay, see you.
All right. Bye-bye.